Thank you very much, Ivan. Actually, it was my pleasure to have you in Zaragoza during the workshop we celebrated, because it was very much inspiring, your lecture, your input to all the students. So I fully agree that these international experiences, these international initiatives are incredibly useful for the students, also for the PIs, also for everybody. And I have to say, I'm learning a lot these days of how transversal is this discipline, is this topic of not science and not theory, and all the things that are around in various disciplines, not only in liquid crystal that it was the one familiar to me, but in other disciplines that you work in, and it's very, very inspiring. So I will go already to the tutorial, but first I will like to present my institution, the Spanish Council of Research. Actually, we are, as Ivan mentioned, we are embedded in the University of Zaragoza, in my institute, that is the Institute of Science and Materials of Aragon. But the Council of Research is a larger thing. It's the largest public research organization in Spain. It's the third in Europe. We are about 14,000 employees that will represent more or less the 6-7% of the manpower of the researchers in Spain, but we produce 20% of the science in Spain. So we are quite productive. We are very proud of it. We have 120 research centers in very diverse disciplines. One of them is material science, and in this type of institutes is our institute, as I mentioned, the Institute of Nanoscience and Materials, that is an excellence center of the Spanish Ministry. Here we are in Zaragoza. For those who want to visit us, please come. It's I will say a nice place, close to, not very far from the beach, very close to the Pyrenees. So it's a good place to visit. And this is my group. This is the group of people that I work with, and these are the guys that are making the things I will present, some besides other things from other groups out from our institute. And at the Advanced Manufacturing Laboratory, in our group, our scientific objective is to design and prepare polymeric systems with functionalities that are of interest in diverse areas. In the past, information communication technology, we are also having some activities in biomedicine, but especially in the last years, we very much focus on soft robotics. And here I go already to the topic of the tutorial, in which I would like to tell you how liquid crystal elastomers allows us to progress towards soft robotic applications, and more in particular, how additive manufacturing techniques are helping us to reach this. But before going into the materials, I will introduce what we understand by a robot. All we are familiar with this image. This is an industrial robotic arm that is, in this case, fixed to the ground. It has links, it has joints, and spread all over. It has sensors that collect information about the position of every part of the robot. They send this information to a robot controller, and this controller analyze this information, process this information, plans, make plans about what to do, and send signals to the actuator so the robot can move and proceed towards its function. The robots, they have different degrees of freedom, and therefore the system can reach different positions. I mean, the extreme of the arm of the robot, where the effector is, it can reach different positions. So this is what is defined the workspace of the robot. Okay, the ultimate goal of a robot is to efficiently perform a specific function or a task. And conceptually, we can visualize a robot as a system that takes information from the real world, for example, from a system that it's interacting with. It sends this. It takes this information, send it to the control. Control make a plan, and send it to the actuators that interact again with the real world, with the physical system that changes and therefore needs to be sensed again, closing this loop that helps the robot to do its task more efficiently in a more precise way. Beside these fixed robots, we have also mobile robots. These are a couple of examples from Boston Dynamics. That's really amazing to see how these robots can move. And in this case, the robot it's mobile, so let's say the workspace is enlarged. So now it's also more uncertain. It's unknown in principle. So these loops of sensing, control, actuation need to become more and more complex and need to be done in a more precise way. So the system can go ahead with its function. Well, I go to the materials. The robots we just saw are mainly made out of metals. They are metallic parts. We are in terms of mechanical properties, we are in the range of hundreds of gigapascals. And if we compare this with the mechanical properties of biological tissues, we are in this range. We are, let's say, in the best case, in the order of some gigapascals in the case of the bone. But if we go to softer tissues, then we go to young modulus in the order of a few kilopascals. So there is a large difference between the materials used in conventional robots and those and the mechanical properties of biological tissues. So this obviously is these materials have to harden. This raises some concerns in terms of the interaction of these robots with when the collaboration of a robot with a human is needed, or when a robot is used to make some action into a body, for example, surgical robots. So this is why softer materials like hydrogels, elastomers, and plastic are becoming interesting, are becoming relevant in order to we want to incorporate this into robots, so that the interaction is softer. And here, this brings me to one of the topics of the tutorial, that is soft robotics. Here you have a soft robotic hand made of elastomeric fingers. These fingers are engineered in such a way, and they have inner channels with void channels that can be pressurized, and when they are pressurized, they are able to grab the hand in a delicate way. So there is a safer interaction with the humans. This is another example taken from the literature. It's again a pneumatic system. The system is engineered. You see that there are differences between this side and this side. So this is what it marks the way it will deform when we apply pressure. And here you see how, by controlling the pressure, the gripper can hold a delicate object, a glass object with a certain weight, something that is not obvious for a conventional rod, for a hard-made robot. So this brings us to the differences between conventional hard robots and soft robots. While in conventional robots, we have metallic parts, rigid elements and joints that pose difficulties to handle difficult, delicate objects. In soft robotics, we use pieces of, parts of the robots are made up of silicone rubber or rubber. They are flexible. They have flexible joints. They are compliant. They adapt to the objects that they interact with, and by deforming, and therefore they are more suitable to handle objects that are delicate or that are changing in shape in a continuous fashion. For example, very soft objects that you take them and they deform while you are taking them. Oops. Okay, besides the pneumatically driven soft robots, there is a strong interest and there is a strong trend on using as a soft robotic material, as a material for soft robotics, smart materials. As you know, smart materials are materials that change one of their properties in a strong way, in an important way when they are excited with an external stimuli. It can be light, can be heat, can be humidity. And these materials can be used to generate soft actuators that are smart polymer systems that respond, that deform in a prescribed fashion when they are excited with this. And among these smart materials, I will go into these three types: hydrogels, safe memory polymers, very quickly, and then I will focus on liquid crystal elastomers. That is the focus of today's tutorial. So very simply, hydrogels, as probably most of you will know, are polymeric networks that are hydrophilic. So in the presence of water, they swell, they increase their dimensions. So if they can change the dimension several times. If you then try to extract the water, try to remove the water, then they diswell again, and therefore they show this material show two-way deformation. You have a reversible effect of the stimuli. As a disadvantage of these materials, they are very soft, and that in certain applications can be good, but in certain applications it's indeed a limitation. And they typically are slow in response because they need to uptake water, and they also due to its very soft nature, they also have a limited ability to make force. Here you have a beautiful example of the group of Jennifer Lewis, in which they printed hydrogels, and they control the deformation of them. Another type of material that is of great interest in this area is safe memory polymers. Initially, you have a material that it has a shape. You heat the material above certain transition temperature. That can be, for example, the glass transition for an amorphous polymer, and then you apply a force and a stress. You impose a deformation to the material, and while you are imposing this deformation, then you cool down the material. So in this way, you program the material and you fix this deformation that is released back to the original shape by heating the sample above the transition temperature. And with these systems, you can program, for example, this is a stent like extractor made out of a safe memory polymer that you program in this just by stretching in the hot state. You cool it down, and then you can by heating you can recover back this stent expanded shape. Typically, they are materials that are one-way deformation, so they are not reversible. And as these big disadvantages that they need this mechanical programming that for complex shapes is not always obvious. Also, they are very nice in terms of tunability of the mechanical properties. Finally, we go into liquid crystalline cross-linked systems, in which I will focus more because it's for the rest of the tutorial. And these are polymeric networks in which the constituent units are messenger, are liquid crystal molecules. And I will skip the rest of the slide intentionally. I will go back later because I want to go back to liquid crystal. It appeared in some of the lectures these days. I remember perfectly Alenka yesterday presented that just for the to make the tutorial self-contained. We try to also give some concepts on liquid crystals. Yeah, most of you know liquid crystals are made out of molecules with a strong safe anisotropy, like this rod-like molecule. And this type of materials, they show intermediate phases between the anisotropic crystal, well ordered, perfectly ordered, the solid, and the isotropic liquid. In the liquid crystal phase, the also named the mesophase, retains the order, in this case the orientational order of the crystal, and has the fluidity of the isotropic liquid. So they are materials that in their low molecular weight version they can flow, but they have anisotropic properties, and this an isotropic orientation of the molecules, and this is translated in anisotropic macroscopic properties of the material. And this is, let's say, the killer applications of the killer application of liquid crystal displays that yesterday was also shown. And essentially, what you have in a display, as you know, is a sandwich, is a thin layer of these liquid crystal molecules between two glass plates, some polarizers, and the important part of the display, the most simple display, the key-end display, the twisted thematic display, is that you are able to control the orientation in the glass surfaces is controlled in a perpendicular fashion in each of the surfaces. The elastic energy makes the work to generate these twists, and by applying an electric field in each of the pixels, you can reorient the liquid crystal here and therefore change the optical properties of the system and play with the polarization, and therefore build in this way the electro-optical bulb that is in each pixel of your display. Okay, going to how we get this orientation. This can be obtained by simply rubbing a very thin layer of polyimide coating in the glass. You wrap this with a velvet cloth in a linear fashion. Then you get grooves. You get orientation of the molecules. You get grooves in the polyimide, and if you put a liquid crystal on top, the molecules close to the surface will get aligned parallel to the grooves, and this alignment, due to the elastic character of the liquid crystal, will propagate this alignment far away from the surface, in particular, typically in the orders of tens of microns. Above tens of microns, there is a limitation. The liquid crystal order is lost and is driven by other factors. It will not follow anymore the orientation of the substrate. So this, as we will see, it will be a limitation in our case. Another method to get alignment in liquid crystals is with photo alignment materials, with photo alignment layers like these polyvinyl cinnamate materials. They are called linearly polymerizable polymers, and this is due to the fact that if we use UV light, if we expose them to UV light, and later we put a liquid crystal on top, the liquid crystal will follow in some way depolarization of the light. Depending on the material and depending on the dose, the liquid crystal molecules can be parallel to the polarization or perpendicular, but in any case, the material is able to register this polarization of the light and transfer it to the liquid crystal. So we can advantageously, you can use photolithographic techniques to generate complex patterns in the polymeric layer that later will be transferred to the liquid crystal that we put on top. Okay, I explain you how to generate oriented surfaces, and we used, I mean, we put there low molecular weight liquid crystal molecules that are in the liquid state. They can flow, they can orient. But if we use liquid crystal molecules that are provided with acrylate groups at the end, with reactive groups at the end, like these acrylates, we can orient them in the liquid crystal in the low molecular weight state, as we saw in the previous slides, and by including a photoinitiator in this system and exposing the system to UV light, we excite the photoinitiator, and then we grow polymeric chains with this. We link these acrylate groups, forming an polyacrylate chain, and fixing in this way the orientation that we got in the low molecular weight. So we can play with the low molecular weight system and generate with this a cross-linked system. This is a technique called in situ polymerization that was developed at the end of the 1980s by our friend Dick Brewer. And now we go back to the slide I skipped before, and essentially what we have is this polymeric network, a liquid crystalline polymeric network, a cross-linked system that, depending on the degree of cross-linking, we call it network or elastomer. Elastomer is low degree of cross-linking. A network is a high degree of cross-linking, and this has an impact in the mechanical properties, but also in the degree of deformation that we are able to achieve. But essentially, any cross-linked polymeric liquid crystalline polymeric system that is cross-linked, when you expose them to temperature, the liquid crystal molecules will tend to orient in a random fashion, as it happened with the liquid, with the isotropic liquid. If you hit a liquid crystal, you go to an isotropic liquid. So you get this misorientation, this disorder in the mesogens, but due to the fact that the mesogens are linked to the polymeric network, this will cause a contraction of the material along the director and an expansion of the material in the orthogonal direction. And I want you to remember this deformation rule because it will be very useful in many of the slides later on. So by temperature, we can get a contraction in the director direction and an expansion in the perpendicular direction. If you cool down the system, the order is recovered, the order of the liquid crystal is recovered, and due to the memory that impose the cross links, then you recover back the original shape. So they are reversible system. Advantageously, you can use a variety of stimuli, as we will see later with some example. They have a relatively fast response. They show, in the case of elastomers, they show a relatively large deformation, and they can exert a reasonable amount of force, bearing in mind that they are soft materials, of course. And here I start, I mean, we already have the materials, we already explained the materials, we already explained some tools of processing these materials, and then we can have now fun. We can go progress towards demonstrating some applications. And here I want to present a work. Actually, it's a long-term project in the group of the Technical University of Eindhoven with Professor Brewer and Professor Danjin Liu, that is an affiliate partner of this institute. And in this case, what they did was to use these reactive messenger, these low molecular weight molecules provided with acrylate groups and dope with a chiral dopant, and then they put this material on top of a substrate, and then the alignment is such. I mean, the treatment of the surface is such that the helixes lie parallel to the substrate. So the liquid crystal is the liquid crystal helixes and the chiral nematic is organized in this way. We can see this material as composed of homeotropic regions in which the helix is, the molecules are pointing upwards, or planar regions in which the molecules are parallel to the substrate. So if we now heat or expose to light and heat this type of samples, then we will have, according to the previous deformation rule, we will have a contraction in these areas and an expansion in these areas. And this is seen in this cartoon, in which you see that the texture blows up from the substrate, what is potentially useful in optics applications. Actually, this very recently, published just this year, bring the group of Eindhoven and Ivan's group to start this and to do this collaboration, in which again, having a substrate and having this type of material, it was possible to generate topological solitons, either isolated or either arranged as self-assembled, solidify them with this in situ polymerization technique, go into a liquid crystal elastomer, and upon heating, you can have these large differences in the surface relief localized at the position of the solitons, having this, as told, potential in optic applications. I mean, this type of protrusions can be felt with the fingers. Okay, but the previous slide was a liquid crystal elastomer fixed to a substrate, but many of the work that has been done in this field relies on actuators that are freestanding, that are not attached to a glass. And here you have a scheme of a TN, of a twisted pneumatic layer, the same configuration that you saw in the display. You have a top layer with an orientation like this, and an orientation parallel to in this direction, and a director in the bottom part leaving the screen. And if you heat this type of film, as following the deformation rule that we mentioned, this will generate a contraction in the top part of the film and an expansion in the bottom part of the film. And the system, in order to accommodate these stresses, it has to bend up, as it's shown schematically here. And this has been used by our colleague in Tampere University, Harri Primäki, to generate an artificial fly trap. Essentially, they have created a thin film of a liquid crystal network, having in this case a splay configuration, but essentially it's very similar. The deformation essentially is the same as in the TN mode. They pierce the film with an optical fiber. The fiber leaves a cone of light, and then when an object passes through this region, or when an object is put in the region, in the field of view of the fiber, that is determined by the numerical aperture of the fiber, then light is reflected or diffused into the film. Then the material is heated, and as a result, it bends and it's able to grab the object, as you can see here. Yep.
Fly traps often store mechanical energy and release it suddenly.
Yeah.
But you're not talking about that, right?
No, it's Yeah,
It's progressive.
yeah, this is the real flight of is a different mechanism, of course. Yeah, this is just the shape and the way that I mean the key point of the actually I didn't went into detail, but the key point of this article of this work is the fact that this construction is able to detect. I mean, it's able to detect the object. I mean, it's not about the deformation. The deformation at this time it was known, but it's a beautiful example how this deformation can be used to generate. I mean, the nicest part of this article is this feedback mechanism that is able to, you are able to integrate in a very simple system a feedback mechanism to trigger a mechanical action. Yeah, but this the real flight of is a bit more sophisticated. Thank you. So here this is a work we did in collaboration with Eindhoven and also in the theoretical and modeling part with Robin Selinger and our esteemed friend Mark Warner and Carl Motes. And in this case, we use a linear photopolymerizable polymer. Remember these materials that are able to register the polarization of the light. And we use a wedge mask like this with an opening, with a triangular opening. And we center this opening at the center of rotation of the sample under the mask. So if now we rotate the mask under this, around this point, and we expose to UV light, you can realize that we are able to generate with this rotation and this azimuthal pattern of the director. So if you now take this liquid crystal cell, I mean, having two glass plates with this linear, with this photosensitive material, you expose through this, you feed it by capillary action with the liquid crystal, and you fix this orientation, you get a texture like this that schematically looks a bit like this. And if now you heat this material, as Mark and Carl predicted, you can imagine that remembering this deformation rule of liquid crystal elastomers, the system will try to contract around a circle and will try to expand along the radius. But we learned in school that this is not possible. We cannot make a circle smaller by increasing the radius. This only can happen if you go out of the plane and turn this into a cone, in which you can make the generatrix of the cone longer and the base smaller. So the system, to release the stresses, can escape into a cone. And actually, if you are, this is if you are indulgent with me, this is flat, not totally flat, but when you heat it up, then you get this cone. Later, we will see better ones. Okay, so this tells us that all these alignment techniques allows us to play with, to program the deformation of this system. Okay, I showed you until now a couple of techniques that based on treatment of surfaces, the surface rubbing, the photo alignment, all of them accomplish the alignment of the liquid crystal by interaction with this surface. But I mentioned before that this alignment propagates only few tenths of microns. So the films we can generate with this technology are in the order of tenths of microns, not more. So the amount of energy available in this actuator is rather limited. It's quite limited. Also, the processing methodology is quite complex. I showed you in the previous slide that you have a sandwich made out of glass. You cure the material, you have to break the glass. Many of the samples die in the process. But I mean, it's like later you need to cut the sample. It's a complex process that, of course, is not suitable for. It's nice for proof of principle, but it's not suitable for industrial fabrication or production. So we thought that 3D printing could be a solution. And as you know, very well know, 3D printing is the addition of material layer by layer to create complex objects. And this being very useful to generate a rapid, to generate prototypes or to generate personalized objects. But typically, the materials that are being used in 3D printer are typically thermoplastics, especially the fused filament type of printers are thermoplastics, and these generate objects that are inanimate, that do not change the shape over time. And here I bring the concept of 4D printing introduced by Tibbits from MIT in the, I think it was 2013, 2014, that introduced the time as a fourth dimension. And many times 4D printing implies the printing of smart materials to generate three-dimensional objects that change over time when they are exposed to the right stimulus. Well, with this in this scenario and in this context, and we developed, we did this in parallel to Professor Taylor Ware in Texas University of Texas, and Jennifer Lewis in Harvard. We developed the 4D printing of liquid crystal elastomers, and for this we generate a main chain polymer made out of these mesogens and provided with acrylate groups at the end. We do this, we generate this macromer, what we call macromer, by Michael addition of a butylamine and a reactive acrylate, mesogenic diacrylate. We have this molecule, we add a photoinitiator, and then we can extrude this material through a needle. We can print it, and after printing it, we can cure it with UV light. As we have a photoinitiator, it triggers the reaction, the polymerization reaction of these groups. So we get a cross-linked system, and we get a liquid crystal elastomers. And we can repeat this process many times and go to many layers, growing into the third dimension. Here you see lines of materials printed at different speed. This is the time I still have. Okay, thank you. Printed at different speeds, and we can see that the higher the speeds, of course, at a constant flow rate, we can get thinner layers, and especially for the higher speeds, what we can check with polarization optical microscope and with dichroism measurements is that we get alignment of the molecules, as you see in the cartoon. So with this technology, we gain digital control of the director, digital control of the morphology of the material. We can control how the molecules are aligned with during the printing process. So we can get later we can release these fibers by using a sacrificial layer of polyvinyl alcohol. We remove the polyvinyl alcohol, just immersing it in water, very simple process, and we get this straight fiber. And when we heat it up, as it is expected, we get a fiber that is shorter, that contracts. And even if you look carefully, you can see that also have some expansion in the perpendicular direction. So this digital control that we have in the morphology is now translated in a digital control of the stresses we have in the printed material, in the liquid crystal elastomer. We can get continuous layers of material by printing adjacent lines of material, and here you more clearly see that the stripe on heating contracts along the director, along the preferential orientation direction, and expands, as you can see in the plot. Due to the additive character of the system, we can generate multiple layers, so we are not limited anymore to these thin layers that we have with the previous technology, with the thin film technology. So we can go to thicker elements, and there we can make a substantial amount of work. So here you have an element that is able to rise a significant distance, I mean, a distance that is, let's say, comparable, I mean, in the same order of magnitude of its own length, and an object that is many times its own weight. Here you have again something. It's a spiral pattern that is a good approximation of the azimuthal pattern that we saw before. And here you see how is the sample at 30 degrees, but when you heat it up, as we explained before, the system goes into a cone. Now it is more clear, more neat, and when cooling, the system recovers the original flat state. So we are able to control these stresses in a quite precise way. We have also embedded these materials in PDMS, in other elastomers. Here you have a ring of our material embedded in a slab of silicon, of polymethyl siloxane, and on heating, due to the asymmetric positioning of the ring with respect to PDMS, we have bulking. I mean, this compression generates the PDMS to bulk out of the surface and generate a lens. Oops. Yeah, and generate a lens, in making the shape of the lens, whose focal depends on the temperature. So, as a wrap up of this part, the digital control of the director allows us to get digital control of the stresses and implement with these actuators, soft robotic actuators that responds to them. Yeah, as I said, we have this, but we have, there is also say, trying to push in the limits of our technology. We see that we have a limitation in terms of the fiber diameter. We wanted to I mean, you cannot go to nozzles that are below 100 microns, because then the pressure is too big, and you cannot generate fibers in this nozzle. So we decided to explore this technique, that is metal electrowriting. Metal electrowriting is a technique developed by Paul Dalton, was released in 2011, and essentially the principle is very similar to that of extrusion, but in this case, a high voltage is applied between the nozzle and the receiving and the collector, the receiving substrate. So a strong electric field is generated in this area. The polymer gets charged, and the fiber is drawn. Even having very little pressure, the fiber can be drawn to the substrate, as we will see in the next slide. And this generates very thin, ultra thin fibers that can be precisely positioned, digitally positioned, like you see here in this polycaprolactone system that was described by Paul Dalton. This has been the main material used in this with this technique. Is a technique that is from the biomedical world, so they use this type of thermoplastic materials. However, we decide to try with our elastomers, and we took our material, the same I showed in the previous slide. And if you have no voltage in between the nozzle and the substrate, nothing happens. The material is not able to flow. But as soon as you apply a high voltage of some kilovolts, then the material appears, and then it gets charged, and it's drawn to the fiber, and at the end we get an extremely thin fiber that we can start to move and in order to generate extractors. And as a result, we were able to get extractors that you can see here are in the order of 100 microns. Actually, we now have much smaller, and there are fibers in the order of few microns, and spaces spacings in the order of 90 microns. You can also build up walls of material and also go to curved structures. Again, as in the case of conventional 3D, 4D printing, this drawing of the fiber towards the collector generates birefringence, generates alignment in the fiber. So again, we gain a digital control of the morphology of the material in our structures that allows us to generate structures that respond mechanically on heating, as you can see in this couple of videos in which you have this auxetic structure that is framed, and therefore it generates this rectangle, or you have this anti-chiral structure that on heating make the nodes to rotate clockwise or counterclockwise depending on the node. Also, the system is able to generate a significant amount of work. As you can see, this small net, spider net, is able on heating to rise this steel ball. Everything I show is up to now relies on temperature excitation, but in order to go to applications, I mean, you saw that the temperatures we used were quite high, so we need to progress towards other types of stimuli, and I will show you a couple of examples. Many of them, all of them have been tested in the past with other technologies, but we are focusing in 3D, 4D printing. So we first go to magnetic materials, and this is a collaboration that we did with Javier Campo, also affiliated member of this institute, in which we included in our polymers hard magnetic particles, and by appropriate dispersion we can generate an ink that can be printed, and we can we can maintain the alignment of the liquid crystal despite the high load of magnetic particles. So we can program the director even having such an amount of particles. That is an advantage that is not possible to do with conventional techniques. Here you have a bilayer, like a PN, like a twisted pneumatic, and on heating, of course, we get this bending, and again the azimuthal sample that turns into a cone on heating. So we are able to keep the liquid crystal elastomer mechanical deformation, the typical deformation, but we have an extra degree of freedom in the actuation, as we have magnetic particles dispersed in the material that we can program with a strong magnetic field. If we now expose our film with a strong magnetic field, we magnetize the sample, we generate magnetic moments in the sample, and this magnetic moment is stable even at high temperatures, the temperatures we use for thermal actuation. So the system we can play with the two stimuli, thermal and magnetic. And now we can play with this, and we can combine these two stimuli. And for example, we can heat the sample, generate some bending, and bend the sample to a certain level, and then apply a magnetic field, an oscillating magnetic field. So you can see that we can reach different modes by combining different temperatures and different voltage, and generate these modes of actuation that are difficult to achieve with one single stimulus. And we try to use this we try to make use of these multimodal capabilities. And here you have an actuator that is a bilayer, a bimorph as the other ones. So by heating it at certain temperature, the cantilever, the cantilever bends. We have put a small mirror here in the cantilever, so a laser reach, and is reflected into the screen. So by changing the temperature, we can move the spot up and down in the mirror. But if we fix the temperature, we center the spot at some point, and now we have this point in the screen. Now, if we put a couple of coils, one perpendicular to the plane of the film and one from the back, and now we apply a small magnetic field in this coil, you get a bending of the cantilever, and then you get the laser in the screen moving up and down. If now we remove this magnetic field and we apply voltage to that current to that coil, then we get a torsion of the cantilever, and then we get an horizontal movement. We can combine both coils and apply a couple of sinusoidal signals, and if they are in phase, then we get this linear movement. But if we now start to play with the frequencies, we can generate a variety of Lissajous figures demonstrating the capabilities of these multimodal, multi-stimuli actuators. We go now to light, because we are being very slow, and we go to light. Obviously, with light you can heat the material. The light, the material absorb. You can dope the material with molecules that absorb light, and therefore light can be turned into heat. So we will be playing the same game as we saw in the past. But we also like to include in our system this interesting molecule. This Asomenzin molecule is a molecule that in the thermodynamically stable state, it has this elongated pro-mesogenic shape, but when you irradiate it with UV light, it turns into this isomerized into this isomer that is not mesogenic. This molecule disturbs the liquid crystal phase, and we, depending on the substituents we have in the molecule, depending on the what we put here in the molecules in these carbons, we can make this more or less stable. But by in the system that we will show you, we have a substituent that make these molecules very stable on time. It can last for a few hours. So if we expose this with UV light, we generate a strong population of these molecules. If we now irradiate with visible light, we turn back, or we leave it, or we heat it up, we leave it back, we go back to the pro-mesogenic shape. So we can incorporate these materials, this molecule in our materials. We expose to UV light, and then even with no temperature change, we expect that something like this will happen. And this was in the literature, but it was not done with this type of technology. So we included this molecule in our inks, and we can see that upon irradiation, we get a strong contraction of the system, also strong heating, as you can see here. But when you remove the UV light, then you get to a level that is different than the initial one, and this level is due to the presence of these molecules that disturb the order in the liquid crystal. This is checked by immersing the system in water. In this work we did it. You put this in water, so the heat is taken by the water. So the heating, the photo-induced heating, is almost negligible, and then almost everything that you see is due to this photochemical component. We have tried to use this to generate a swimmer, an ephira, that is a baby jellyfish. This creature swims by suddenly moving the lappets down. So it generates a vortex in the water, and it propels up, and later it makes a slower movement to recover the shape. So in this way it can swim forward. And we have to try to mimic this structure by 4D printing, by 3D printing with our photosensitive material, this structure, and taking advantage of the fact that when we radiate with UV light, we have a strong absorption in our film. So light is primarily absorbs in the first layer and does not reach much to the top layer. So to generate this population of these non-mesogenic molecules in this region, and all trans molecules in this region. So the system, to accommodate these stresses, bends towards the light source. So by doing this, we expect to have this swimming motion, and by using green light, we want to go back to the system. And this is after some optimization. This is what we got. This is the little LCE, liquid crystal elastomeric ephira, that is being sequentially irradiated to UV and later on to green light to relax. And you can see how it can propel up with just with the light. Now we jump finally as a last example to a system that is purely photothermal. It's this Crystalline system that was a very good surprise to us, because we just wanted a dye for photothermal actuation. But in preliminary experiments, we saw that the system was changing color, and we thought it was a degradation. But after a while, the system goes back to the initial color. So it was something to a large extent, it was reversible. And after some, what we saw is that, yeah, on irradiation with green light, we generate these bands in the far red and infrared, near infrared region. And what we discovered that is due to the formation of radicals, as we can see by electromagnetic paramagnetic resonance. Yeah, by irradiating with infrared, we recover back the original spectra. But you can see the difference between the virgin sample, that it does not absorb or absorb very little in the far red, and the sample that has been exposed to green, that has a strong absorption in this region of the spectrum. So with this, we have a system, the original system, that is not sensitive, or very little is sensitive, but not too much sensitive to far red light. And the, let's call it program system with green light, we have a system that absorbs a lot of far red light. So we can excite with far red light the system and get a strong deformation. So with this, we have used it to program to program these materials. In the unprogrammed version, here you have the spiral, and when you irradiate with far red light with sufficient intensity, the absorption is low but sufficient to generate the cone. But if now we pattern the material with this annular mask, we generate radicals in the central part of the sample. And if now we expose to far red light, what we get is a strong deformation in the middle that generates quickly a cone. But the outer part of the annular part of the object cannot follow, and then generate these undulations along the azimuthal direction. Once the radicals are consumed, once the radicals go back to the normal state, then the system recovers essentially the same configuration. I finish, and I think more or less in time. I hope I showed you that we can integrate different functions with additive manufacturing that allows us to get more complex, much more complex architectures, also in the small as small structures by using melt electrowriting, and this together with the scalability, the reproducibility of additive manufacturing techniques, make these technologies a key enabled technology for the further development of soft robotics. Just thanks the funding agencies, the institutions, of course, again, the SKCM² Institute, and thank you very much for your kind attention.
Thank you for this wonderful lecture. Do we have questions?